Thanks for coming to our session on vSphere compute and memory. Today, my name is Songbum, by the way, and Faye is my colleague, and we will talk about CPU scheduler in vSphere and memory scheduler in vSphere. We hope to provide some useful tips for you and clarify a few confusions. Let's get started. This is the disclaimer slide. I believe you've already seen this a couple of times, so let's move on. Yeah, I'm going to talk about CPU part. I first want to start talk about how to set the right expectation on VM performance, and then I'll talk about ready time. On CPU side, ready time is pretty important, and on some comment on VM sizing, especially how many vCPUs should you configure per VM. Then I'll briefly talk about NUMA and virtual NUMA. So you have to set the right expectation on VM performance. If you understand your application behavior and understand virtual environment, then I believe you can set some reasonable expectation. And if your VM performance is worse than that, then maybe you can do something, some tunings or config fixes to improve that. Let me first explain what will happen. Your VMware application becomes busy from idle state. Let's just say your application is web server. And on the left side, I'm showing 4 different modes of execution. So on the top, there's a kind of VM mode. It's kind of weird name, but basically it executes VM instructions. And at that level, it runs at same speed as bare metal. And whenever some virtual event happens, which I'll explain later, the CPU switches mode in special mode, and then trying to emulate the virtual event. And sometimes hardware emulation is not sufficient, so it needs hypervisor support. So VMM stands for Virtual Machine Monitor, and we can consider it as an hypervisor. And your VM runs on top of an operating system, so this VMK or VM kernel, you can consider it as an operating system. So let's say your web server was idle, and then there was no new incoming request. So there is a packet arrived in network card, and then it generates interrupt, right? And then interrupt has to be serviced by VM kernel. So by the way, time progress from left to right. So black bar shows the time spent by VM kernel, and it services the interrupt, and then it changes the vCPU state to ready. It basically wakes up the vCPU, and it schedules vCPU, meaning find the best pCPU or physical CPU for this vCPU. And in case where there is no available pCPU, that means we have to put this vCPU into ready queue, right? So in this example, VM kernel spends some time, and then vCPU spends some time in ready queue. Then it finally finds pCPU, then it starts running. So green bar shows the progress of VM. So this web server may execute instructions like add and read memory or doing some computation. Those instructions runs at the same speed as bare metal. Okay. And then let's say there's some event happens like executing privileged instructions. What is privileged instructions? Well, for example, the VM trying to update CR3 register, mostly from context switching, and it may incur TLB miss. How many of you have never heard about TLB? Okay, good. We have very technical audience. So TLB, for briefly, it stands for Translation Lookup Side Buffer. You can consider it as a small cache on the processor that remembers the mapping from linear address to machine address or physical address. And for those events, it has to be handled first. CPU tries to handle it in hardware level. So it spends some time in a special CPU mode. By the way, VT is for Intel and AMD for AMD processor. And if hardware cannot handle it all, then it changes mode to hypervisor. So it spends some time in hypervisor and finishes the emulation or handles the event correctly. Then it goes back to VM mode, and then again runs the same speed, like 100% of bare metal. And then let's say web server wants to do I/O. Then for device emulation, again, it goes down to hypervisor and spends some cycles. And again, it goes down to VM kernel to issue I/O to I/O threads. It doesn't necessarily wait until all I/O operation is finished. It simply issues the I/O, and VM kernel threads or I/O threads will get the job and then start the processing. Then your vCPU can immediately go back to VM and continue whatever work remaining. Okay. And you handle that request, and then there's nothing else to run. Then guest executes a halt instruction. And halt instruction is kind of special because it gives us a signal that VM has nothing else to do. So it's a good time to give this CPU resource to other VM. So in that case, VM kernel deschedules vCPU and change the state to idle. So from this figure, the point I want you to take away is anytime the VM spans in green bar, that means the same speed as bare metal. And in most cases, this green portion is large enough so that you don't see very high virtualization overhead. But whenever there's a gap, that's a source of overhead. So if your application tends to have that gap, or your virtual environment consolidation is too much, then you will start seeing performance slow down. So let's say you notice that your application is slower in VM. What's going on? Then whenever I kind of do a performance debugging on customer issues, I first start to understand application behavior. So how many kind of privileged instruction does it execute? Or does it do a lot of context switching, or does it do nothing but context switching? Or will it generate a lot of TLB misses? Something like that. So I already mentioned that about TLB misses. So using large pages inside VM or on the ESXi host definitely improves the performance when TLB misses happen a lot. But still, there is an overhead associated with it. By the way, large page is enabled by default on ESXi, and Faye will talk more detail about it. Your application may be virtualization friendly, but you can still see performance issue because of resource contention, CPU contention or memory contention. And CPU contention, ready time tends to be the best indicator. And if you have a host level memory swap, the performance impact can be pretty significant. So you want to watch out for that. So what is the reasonable expectation on VM performance? Well, if your application behaves nicely, you don't have any contention, it is almost close to 100%. Sometimes 95%, 92%, but that's my expectation. And in most cases, a little bit of contention is okay, and then most application, I would say around 90%. And well, if it is lower than 80%, then I would start wondering maybe there can be some config issues or something can be done to further improve performance. Worst case, some applications are hard to virtualize, basically. If it generates a lot of TLB misses, the impact can be significant. And if you overcome your memory too much, there's no kind of lower limit. So let's move on. Yeah, I previously mentioned that ready time is a good indicator for CPU contention, but not always. So I want to talk about that because sometimes customers are pretty puzzled. I'm running only one VM, and I'm seeing ready time. Am I crazy, or what is going on? Ready time can happen without CPU contention. So, on this same example, let's say, let's use the web server example again. Let's say on T1, web server becomes busy, so we need to schedule it. So A stands for scheduling cost. So we have to, CPU scheduler has to run before vCPU starts running. And it can spend time in ready queue, so B stands for the time spent in ready queue. And between T3 and T8, it represents actual execution time. Let's say at time T4, the interrupt happens to that particular vCPU where vCPU was running. Then vCPU has to stop, and then VM kernel has to service the interrupt. So D stands for interrupted time. During that time, vCPU cannot make progress. And let's assume that this VM was actually running on hyper-threaded system, and you used to run alone, meaning it can use all the core for itself. But at T6, the partner vCPU becomes busy. So now you have to compete for the single core. And you run at about 50% speed or 62 or around 60% speed. It depends on the workload. Anyway, so efficiency becomes lower, and CPU scheduler has to account for that as well. The most important point I want to take away from this slide is ready time is not just time spent in ready queue. It also includes CPU scheduling cost. So that's the most important part. And runtime is time between T3 and T8. And note that runtime includes interrupted time, and also runtime doesn't necessarily mean the same speed. It may run at slower speed. Overlap time stands for the interrupted time, and if that particular interrupt is for the same web server VM, then we have to add it to system time. Use time looks very complicated. It's basically runtime, but we want to account for system time and also interrupted time and some efficiency loss as well. So yeah, I don't think we have to memorize this formula, but have just some basic concept about actual charging may be different from runtime. So let's go back to ready time again. So when you see high ready time, what is going on? This I'm showing you a kind of ideal situation where you pay some scheduling cost, but your runtime is long enough, maybe, I don't know, tens of milliseconds. In such a situation, the scheduling cost is low enough and then can be amortized, and your ready time is close to zero. If your vCPU spends some time in ready queue, then your ready time will be dominated by component B, or time spent in ready queue. In which situations you'll have this? So actual CPU contention, meaning more active vCPUs, or virtual CPUs than your physical CPU. And maybe you set a CPU limit and forgot about it, or you set shares, CPU shares to some value, but other VMs have much higher values. And how many of you use CPU affinity, by the way? Okay, I hope what you're doing does not cause artificial CPU contention, but please be careful. My general recommendation is stay away from it, but if you know what you're doing, then yeah. The third situation is interesting because, again, back to the example of I'm running just one VM and I see ready time of 10%. What's going on? Your runtime, the VM's runtime can be very short, and say sometimes millisecond or even lower than that. and then the sleep and wake up pattern or sleep and wake up event happens very, very frequently. So the VM runs very short while and then goes back to sleep, and almost immediately, it is woken up again and then runs very, very short, and then repeating this process. This is pretty kind of bad situation. And in such situation, you can have high ready time, and the one indication you can watch out for is how many wake up does it have. So what you can do when you see high ready time, if you believe your VM doesn't have frequent sleep and wake up, and you suspect some CPU contention, then I would first check DRS issue. So your DRS may be set to manual. You may want to change it to automatic. Even if it is automatic, the parameter may be too conservative, or maybe it's time to add a new host or more host. And again, there are other issues like resource setting, like CPU limit and shares. What about the second case, when you don't suspect any CPU content, and it seems to be dominated by scheduling cost? Ideally, application, instead of doing a very frequent sleep and wake up, maybe it can consolidate tasks so that it can increase runtime to amortize scheduling cost. But it is not always possible to change the application behavior. There are two tunings you can try. I will not go into detail about these options. You can Google it, or it is well documented. And I personally prefer the first approach, idle loop spin microsecond. The idea is you spin a little bit waiting for the next event instead of giving up your vCPU to VM kernel. I like it because it is better for consolidation. You can pack more VMs, basically. I often got questions like, okay, give me some threshold on ready time so that I can watch out for. Is it 5%, 20%? What is the value? What is the magic number? I don't have that, unfortunately. And I have to answer, that depends on the situation. I have a few slides that'll kind of make the point. So even if the ready time is same, performance impact is different. How? So here I'm showing you a chart. It's basically the impact of ready time on throughput. Okay, to generate this data, I've run Java workload, which is throughput oriented, and I pin that VM with the background workload, and I change the load to cause ready time, and they have same shares, everything same. And in the chart on the x-axis, ready time changes from almost close to 0, so no contention, to about 18%. And on the y-axis is the normalized throughput, so higher means better. And as you can see from the chart, the impact is almost kind of proportional. So if you have a 10% ready time, the throughput degradation is about 5%. So it's kind of straightforward. Impact on latency is pretty interesting. Again, the methodology is the same. I've run some latency sensitive workload and pinned it with background workload to cause ready time or to cause contention. And then y-axis here is a 99.99 percentile latency. And some people call it tail latency. And there are two lines. Red line is flat and blue line is spiky. What does it mean? It's corresponding to different types of background workload. So with spiky background workload, the workload becomes busy more frequently, but it stays busy shortly. So it becomes busy and then quickly goes to sleep, and then it becomes busy again. And flat workload is you can see the red bar. So it becomes busy less frequently, but it stays busy longer. Okay? And I tweak the load so that both data points have similar ready time. And if you see the rightmost data points, both cases ready time is about 23%. And with spiky background workload, tail latency is about 13 milliseconds. But with flat workload, it's about 16 milliseconds. So there is a 3 millisecond difference. Okay? And ready time is the same, but it depends on how background workload stays busy or interferes with this latency sensitive workload, and the impact can be pretty different. If I look at 90 percentile latency, regardless of ready time, they are under 1 millisecond. So if your workload is very sensitive to tail latency, then you may want to watch out for ready time. Okay? Even with, say, maybe some people may tell you, I don't know, 10% ready time is okay, but it may be not for your latency sensitive workload. And some may tell you, 15% ready time is horrible, but maybe for your workload it's fine. So I understand this is not simple, but yeah, that's the thing. I've seen a few customer complaints about ready time. The symptom is you are running, the workload I've experienced is Microsoft Exchange, but it can happen to other VMs. So the symptoms are you have 2 NUMA nodes, or maybe more NUMA nodes, but VMs are placed on 1 NUMA node, and then you see ready time. And the other NUMA node is pretty idle. So people are upset, first because you were told that ready time is really bad, and you see the other NUMA node is idle. So I've seen a few customer cases. And it is by design, because those VMs are sharing data, and sharing data on the same NUMA node is much more efficient than kind of ping-ponging data across NUMA nodes. So you may see some ready time, but it's actually better in the end-to-end performance. The idea is it is better than running less efficiently or slowly on separate NUMA node without ready time. But some cases we see current or previous policy is too aggressive. So on 6.0, we added a small change to make the policy less aggressive. So the idea is, okay, if we consolidate VMs, make sure we leave at least 10% CPU headroom so that it won't cause ready time. So I hope to make that change, kind of help remove customer concerns. Anyway, so and if you don't like the policy, I used to have an option to completely disable it, but I like this option better because it kind of gives you control how much CPU headroom you want to leave. Okay. So something you may want to look at. Let me talk about sizing. Oversizing VM is wasteful, wastes CPU resource, and hurts performance even. Okay. So I've shown this similar chart before, but let's say your application owner demands like 32 vCPU VM because his or her application is so awesome, but ends up using only 2 threads. So that means 30 unused vCPUs. And then this chart shows CPU overhead per vCPU. Okay, I've run a 64 vCPU VM and measured the overhead and divided by 64. Okay, so this is per vCPU overhead consumed by unused vCPU, and it depends on OS and timer setting. Most overhead comes from processing timer interrupt. Anyway, so it can be pretty significant. Red 5 1 kilohertz timer is about 12.5%. Okay, it's not free. But the second point is more important. So oversizing VM actually can hurt performance. For this, I've run single-threaded application, in 1 vCPU VM, 2 vCPU VM, up to 64 vCPU VM. It's the same workload. And on y-axis, it's again normalized throughput. So higher means better. And you can see the performance is progressively worse. And performance drop can be as much as 20%. It's non-trivial. You burn more cycles, and then you get worse performance. Why? I don't investigate it in very detail, but my suspicion is you have more vCPUs, guest schedulers is more tempted to do migration, and process migration across different vCPUs is expensive. Let me talk about NUMA. So ESXi is optimized for NUMA, yes. How many of you have never heard about NUMA or what NUMA is? Okay, so NUMA stands for Non-Uniform Memory Access System Architecture, because basically you have, I don't know, 2 NUMA nodes, 4 NUMA nodes, and accessing local memory versus remote memory, the latency is different. So key point I want to make here is accessing remote node can take, I don't know, 30% longer to 200% longer. It depends on system type. ESXi schedules VM for optimal NUMA performance. So what do I mean? Let's say you run VM with 6 vCPUs, or 1 vCPU, or 4 vCPU. In this case, NUMA has 6 cores, right? So ESXi sees it, and then, okay, I can schedule it within 1 NUMA node. Okay, so I will make sure I'll schedule compute and memory on the same node. So what that means is guest OS or application can be agnostic about NUMA or whatever. Okay, it can place process and memory anywhere. ESXi just optimizes for automatically and transparently. So that's kind of pretty good situation. What if your VM is big or wide? So in this example, you have a 12 vCPU VM and running on 2 NUMA nodes. And this is a kind of hypothetical example where virtual NUMA is disabled or not available. And in this situation, VM doesn't know about NUMA system. It thinks it runs on top of UMA system, or Uniform Memory Access System. So that means it may schedule a process on one node, allocate memory on the other node. So memory locality becomes worse. That means you pay more penalty. What virtual NUMA does is ESXi exposes to VM that it is running on top of 2 virtual nodes. Then guest OS or application that is aware of NUMA topology or optimized for NUMA system, it does the right placement of compute and memory. So meaning that process and memory will be allocated on the same virtual node. Then ESXi makes sure to preserve that locality for best performance. So virtual NUMA is pretty important for high performance on wide VM or big VM. There are some options, but the best practice is stay using default. Stick to vNUMA default. Yeah, I'm going to talk about cores per socket. On the figure, I'm showing you a 36 vCPU VM. I was creating a 36 vCPU VM, and the default is cores per socket. And you can see there are 36 virtual sockets. It's pretty weird kind of configuration, but that's the default. And if you change cores per socket, that means you change virtual NUMA size. And it is very easy to make mistakes. And virtual socket size, my personal opinion is it doesn't have a big impact on performance. But virtual NUMA size has a significant impact. So you don't want to make mistakes in virtual NUMA. And ESXi picks in most cases, it picks the best virtual NUMA config for you. So you don't want to change it. But I understand that Windows licensing or other licensing is tied to virtual socket count. So you don't want to unnecessarily pay more for those virtual sockets. So in that case, I thought about it, what is the best practice you can do. What I would do is, I want to first know what virtual NUMA ESXi picks for me for a given system or for a given hardware and for a given VM. Because virtual NUMA depends on system size or NUMA node size and also VM size or how many vCPUs that VM has. Here's an example. Let's say you're running a 20 vCPU VM. And you want and the system has 10 cores per node. So you want to first know vNUMA size. Okay? So let's say maybe I can power on one Linux VM, and there's a tool called NUMA-CTL. You can actually check the vNUMA size, and it'll be 10. Okay? So now that you know vNUMA size is 10, the default setting, in default setting, you will have 2 virtual nodes, and each virtual node have 10 virtual sockets. It's pretty weird because modern CPUs have either one node per socket or 2 nodes per socket. But in the old days, IBM system, when Intel doesn't have on-chip memory controller, even AMD, they have one big board with the multiple sockets, and then that's one NUMA node. So this virtual topology or default virtual topology follows that kind of old IBM system model. So I understand this is kind of counterintuitive. But again, once you know virtual NUMA size being 10, then just set cores per socket value to 10. That will make one virtual socket per one virtual node, or vice versa. So in that case, you will only have 2 virtual sockets. Okay. Then you don't have to worry about different vNUMA size or changing vNUMA size. All right, so one final point. So enable CPU hot add option. If you enable it, then it turns off virtual NUMA. So you have to consider the impact of that. So let me summarize. Being able to set the right expectation is important. Ready can happen without CPU contention. And impact can be different. So, tail latency is sensitive to ready time. Do not oversize your VM and stick to virtual NUMA default. This is a CPU schedule white paper. It has a section for NUMA as well. So I hope that should be helpful. Let me hand over to Fei, and he'll talk about memory management.
All right, in the second part of the presentation, I'll start with some basic ESS memory management concepts. And I'm going to talk about some interesting topics, including how to size your VM, what is the difference between reservation and pre-allocation, the interaction between page sharing and large page, some VM memory overhead in terms of per VM overhead and per host overhead. Finally, I want to give some guidance about how to safely memory overcommit to your ESS host. Well, in the very beginning, I'd like to start with some terminologies that I'm going to use in the talk. Basically, VM memory size of the VM or host is typically the total amount of configured memory. It can be divided into allocated memory and free memory. And the allocated memory can be further divided into the active memory, which by definition is the allocated memory that are recently used or touched, and idle memory, which is obvious, the allocated memory that are not recently accessed or touched. So the scheduler will treat the active memory and idle memory differently. Well, the task of the memory scheduler is kind of pretty straightforward. It computes the memory entitlement of each VM and reclaim the guest memory from the VM if its entitlement is less than its consumed memory. Otherwise, the scheduler simply does nothing because everybody is happy. Well, to compute the VM's entitlement, The computation is based on some the VM's config parameters, like the VM's reservation, shells, limits, and also the memory demand of the VM. The memory demand is determined by the VM's active memory. Since ESS doesn't know exactly the working set size of the workload running inside VM, so it relies on a statistical sampling technique to estimate the active memory. The estimation is typically pretty accurate. From performance perspective, the goal of the memory scheduler is try to handle the transient memory pressure well. So as what Samuel mentioned before, I like to emphasize, please set the right expectation on the ESS memory performance. Because if your host suffer from the constant memory pressure, we should consider the high level, like cluster level load balancing algorithm like DLS, or just simply remotion some VMs out of the box. ESS trying to reclaim some memory from the VM, it first check the memory state of the host. What a memory state is associated with is mainly determined by the amount of free memory that are currently available in the host. For example, if one host is just booted, it has plenty of free memory, it stays in the high state. Well, as VM start to consume the memory and the free memory is getting smaller and smaller, when the free memory drops below a certain threshold, which we call mean free, as you can see, the memory states change from the high state to low state. In high state, we only use page sharing to reclaim the memory, while in low state, in addition to page sharing, we also use ballooning, memory compression, and host swapping to reclaim memory from the VM. And compared to the cost of the page sharing, those three techniques are pretty expensive. I'm not going to talk about all the details about the different memory reclamation techniques, different memory states, due to time constraints. Here I'm pointing out the paper. Every concept that I've mentioned so far explained in great details in this white paper. So just please take a look if you're interested for the details. Well, I've seen cases that people think reservation and pre-allocation are the same. But in fact, they are different from many aspects. The reservation is typically used in admission control and the entitlement calculation. Setting reservation doesn't mean that the memory is allocated. For example, if you can set memory reservation for 2 GB VM, you set 2 GB memory reservation, but during the VM's entire lifetime, you may see that the VM never used more than 100 megabyte memory. That's entirely possible. So by setting reservation, so the hypervisor just guarantee that the reserved amount of memory will be kept in the physical RAM if the VM is used of them. Whereas pre-allocation is different. So if the VM is given the pre-allocation option, the VM's memory is reserved, fully reserved, and fully allocated after the VM is powered on. So this feature is mainly useful for latency sensitive workload because some people just trying to completely avoid the overhead of the memory allocation. Well, we should be very careful here because when you set pre-allocation to the VM, the hypervisor cannot reclaim any memory for such VM because the memory is fully reserved. So if your VM's setting pre-allocated everything, but you just use a small portion of it, the rest of the memory is completely wasted. So, all right. About the sizing of VM is always tricky because if your VM's memory size is too small, you may suffer from gas level swapping, which is pretty bad. While on the other hand, if the VM's memory size is too big, your per VM overhead is getting higher. So basically, so the VM's the memory size should be set being higher than its peak memory demand. So in order to completely avoid gas level swapping. So another benefit of lowering the memory demand is that if necessary, you can just set a reservation above this memory demand. So the host level, the memory reclamation, like host swapping, can also be avoided. Here I show an example of how to get the memory demand information from the vRealize operation, the tools. In this particular example, I showed the gas memory demand of my workstation VMs in the past 24 hours. As you can see, the memory demands vary between 244 megabyte and 65 megabyte. So since my workstation VM is almost idle, so the memory demand looks very low. Well, the key point here is when you size VM, the VM's memory size should be set based on its memory demand. Peak, yeah. Page sharing is a nice technique to save memory, but some of you may already know that when you host have large page enabled, the page sharing doesn't happen. So I'd like to take this opportunity to clarify some interactions between the page sharing and the large page. Well, first I want to say that the memory saving from page sharing can be quite significant for homogeneous VMs. So in these two examples, I use multiple swing bench and the VDI VMs. So it turns out that there were about 43% memory for swing bench VMs and 75% memory for VDI VMs. The memory can be shared. And in terms of sharing, there are about 34% memory for swing bench and 73% memory for VDI workload can be saved from the page sharing. So the sharing can be quite significant. Well, some features can prevent sharing from happening. For example, some guest operating systems use the ASLR, address space layout randomization, for security purpose. So this feature, study has shown that this feature may reduce about 50 MB of sharing, but this number is pretty small if your VM is memory size is big enough. Well, some Windows typically use superfetching, which is a technique to proactively cache in some files from disk into the memory. So this feature indeed largely reduces the amount of page sharing. Well, in reality, we find that sometimes this feature causes a lot of IOs, which in turn that hurts VM performance. Therefore, in our VDI environment, we actually recommend to turn this feature off. Again, as I mentioned, if your host uses large page sharing doesn't happen. This is because our ESXi hypervisor doesn't share large page due to performance reasons. Although the pages are not shared, but the background, the page sharing scanning thread still works. Basically, still generates the signatures for the small pages within the large page range. We do this because for whatever reason, if the large page is broken, so with these signatures available, we can quickly share those shareable small pages. You may be a little bit disappointed about large page because, with large page, we don't share any pages. It sounds bad, but why do we use large page in the first place? It's mainly because it can improve performance for many workloads that due to the fewer TLB misses and the faster page table lookup time. For example, compared to the baseline case where both the guest and the host use small pages, when both host and guest use large pages, the performance of SpecTLB workload can be improved by 30%, which is pretty significant. Due to the performance advantage, so ESS choose to enable the large page by default. Then how large page impact on the memory overcommitment? Clearly, when we use large page, the memory pressure is getting higher because there's no pages shared. However, a large page will be broken when any of the small pages within the large page is ballooned or swapped. So after large page is broken, then the sharing will happen thereafter. I'll give you an example to see what happens when the host running swing bench VMs and the host memory is getting overcommitted. So this figure looks a little bit complicated, but the key point here is when host memory is overcommit and the ballooning and the swapping happens, the total amount of the large page in the host, which is shown as a yellow line, is getting reduced. This is because large pages are broken, and the page sharing happens thereafter. So essentially, when using large pages, large pages default delays page sharing until the host memory is overcommitted. So smart people can see there's a problem here, because when page sharing happens, then ballooning and swapping has already happened. This may already hurt VM performance. Can we do a better job here? So in our latest vSphere 6.0 hypervisor, we introduced a new memory state we call it clear memory state between the high state and the low state. So although the naming may not look perfect, clear, well, what it simply does is when free memory drops to the clear memory state, the ESX will proactively breaks the large pages that contain shareable small pages, so that those small pages can be shared right away. Then we can reclaim free memory through page sharing. The whole purpose is trying to avoid the host from entering the low memory state, which triggers the very expensive ballooning or swapping. Well, if the host free memory goes back to high state again, those small pages will be promoted to large pages again. Basically, this feature trying to make the best use of both small pages and large pages. This figure shows the performance benefit of having the clear memory state. In this example, I run about 12 VDI VMs, which consume almost all the host memory for about 50 minutes. Then I start to power on extra VMs to introduce the memory pressure to the host. In the figure, the y-axis shows the average operating latency. So the lower, the better. The x-axis shows the number of the actual VMs that I power, which indicates different level of the host memory overcommitment ratio. In the figure, I compare the performance between ESS 5.5 hypervisor, which just uses a default large page, and the ESSi 6.0 hypervisor with clear memory state support. In the figure, as you can see, when we as the number of actual VMs increases, the latency can be increased by about 30% with the ESS 5.5 hypervisor, whereas the latency is almost not impacted at all for ESS 6.0 hypervisor. The reason why 6.0 has such a good performance advantage can be explained in this figure. If you look at the total amount of shared memory in the rightmost figure, you can see that with a clear memory state, the page sharing happens much earlier, and so that the total amount of the balloon and the swapped memory is completely avoided, as shown in the middle figure. Well, in the ESS 5.5 hypervisor, the sharing only happens when ballooning and the swapping happens. So those swapped and ballooned memory already hurts performance. We have published an academic paper to talk about all these new features technically in great details. So I'm just here to give a pointer if anybody is interested in the details. Okay, overhead memory is a factor that you cannot just simply ignore when you consider consideration, because virtualization comes with the cost. When we talk about the overhead memory, typically there are two types of overheads. One is per host overhead, and one is per VM overhead. And both of them are composed of many, many, many components. So here I show you an example. This is the tree map breakdown of the VM kernel overhead in an idle host. As you can see, there are a lot of components. Each block indicates the overhead components, and the size of block indicates the relative memory size of that components compared to the others. Among all these components, some of the components, the sizes are scaled with the host memory size, well, with a different ratio. Some components, they are static overheads, so they never change. Basically, with given these complicated components, it's almost impossible to conduct a very accurate formula to tell, what is the memory overhead would be. Although I didn't show the figure, but the same applied to the per VM overhead as well. The accurate formula is not possible. Certainly, of course, we can come with some experimentally safe estimation. So I want to emphasize here that all the numbers I showed in these slides come from some internal test, the results from some internal test. You probably will see different value in your test environment, and all this value I would say very conservative. Basically, for per VM overhead is typically less than 10% of the configured VM memory size. For host overhead memory, I use a slightly different metrics. Basically, if your host is less than 64 gigabyte, if you use less than 90% of the host memory, you should not see any noticeable performance impacts due to memory reclamation. Well, for hosts with larger than 64 gigabyte memory size, such threshold is 95%. Again, I want to emphasize that all these numbers are pretty conservative. I would assume that you guys should see less overhead in your working environment. All right, finally, I'd like to give some guidance about how to safely memory overcommit an ESS host. Well, before answering how to safely overcommit, I'd like to refresh some concepts about active configured memory overcommitment and active memory overcommitment. So by definition, the configured memory overcommitment is the sum of the configured VM memory size divided by the host memory size. And active memory overcommitment is the sum of the active memory of all the VMs divided by the host memory size. So if the active memory overcommitment is close to 1, it's very likely that your host will suffer from performance degradation because some of the active memory are not in physical RAM. Well, if configured memory overcommitment is larger than 1, as long as the active memory overcommitment is less than 1, the performance impact should be very trivial. It's negligible because most of the reclaimed memory come from the either free or idle guest memory. Given that, the general principle of when you do memory overcommitment is we should always target high consolidation ratio. Well, keep the active memory overcommitment less than 1. Well, people may ask, oh, how do I know the active memory? As I mentioned before, you can try to use the vRealize operations to track the VMs, the average and maximum memory demand, so which is pretty good proxy for the active memory. And what if I have no idea about the active memory? Then, the last thing I can do is you can just keep adding the VMs and watch for some performance counters to see if you hit any performance problems or not. Then you may just curious what these counters are. But before talk about what would it be the counter to watch, I'd like to first talk about some counters that they should not look because it may cause a lot of trouble from both of us. The first counter is the consumed. This counter sometimes is very misleading and confusing because people say, oh, my VMs has very, very little consumed memory. Is it a problem or not? I would say consumed counter itself doesn't mean anything. So your VMs has very small consumed memory. It can simply because your VM has been sitting idle for a very long time. Then all the free memory has been reclaimed by the hypervisor. Where since your VM is idle, it doesn't have any performance impact. Another set of counters are reclamation-related counters, which tell you the amount. For example, the ballooned amount, the swap user amount, compressed amount, and shared amount. A non-zero values for those counters does not necessarily mean that your VM has a performance problem. I'll give you an example. So in this example, I run 6 4GB swing bench VMs in a 16 GB host. 3 VMs out of 6 VM 4, 5, 6 keeps idle during the whole experiment. And the top figure I show the operation per minute, which is a performance of the swing bench workload over execution time. And the bottom figure I show the counter values for all the counters I mentioned in the previous slide. In the experiment, I will start to run VM1 for 10 minutes, and I'll start to run VM2 for another 10 minutes. At this moment, the memory is not overcommit. As you can see, all these counters are almost 0. At time 20, I start to run VM3 for just 10 minutes. At this moment, the host memory is overcommit. As you can see, we show a big jump on the ballooned memory and some memory on the some shared memory. Because memory is overcommit. But since VM3 only run 10 minutes, then after VM3 finished, the host memory is not overcommit. Well, but if you look at all the counters, the ballooned amount and the swapped amount keep the same. Well, even though the host memory is not overcommit, by looking at the performance of VM1, VM2, compared to the case when it runs alone without any other VMs, the performance difference is 0%. There's no performance impact at all. This is because all the reclaimed memory coming from the 3 idle VMs. So, which means just by looking at those 4 counters, you cannot identify the performance problem. Then what will be the counters to look? The first counters is the swapping rate. So if your host shows a constant swapping rate, which indicates your host has a performance problem. The second counter is the latency, which shows a percentage of the time from the VM kernel perspective. The VM kernel waits for the memory decompression and swapping to finish. So this roughly estimate the performance impact due to the memory compression or host swapping. So if the latency, if your VM shows high latency value, which indicates your VM will have a performance problem. And the next counter is active. Basically, if your VM's active memory is very small, it is less likely the memory reclamation will cause performance problem for this VM. Again, I show you an example of this. So similarly, I also run 6 StreamManage VMs in the 16 GB host. Run VM1 for 10 minutes, then start VM2 for another 10 minutes. So at time 20, instead of just running one VM, I start all the other 4 VMs at the same time. So which push a huge memory pressure on the host. As you can see, the host shows a very constant swapping rate value. By looking at the performance of VM1 and VM2, you will see a very, very high performance degradation due to the swapping. So the key point here is you can use this swapping rate as an indicator to show that if your host has a memory problem or not. All right, the key takeaway of my talk is please track the memory problem using the right counters like swapping rate, active, and latency. And the VM memory should be sized based on the memory demand. ESS hypervisor is trying to do a good job on reducing the overhead memory, try to keep it as single-digit overhead. The new ESS memory management features improve performance. Finally, I want to emphasize this is, again, ESS hypervisor is designed to trying to handle the transient memory pressure well. So if your host has a constant memory pressure, please consider high-level load balancing algorithm like DIS. All right, thank you so much, and please fill out a survey if you can. We are happy to take any questions.